So everyone, Assalamu alaikum. Inshallah, we will start now today the DAC specification. The lecture today, we will have the DAC specification. And before we start, again, I am telling, and now we have 23 students. Some students, they are not punctual to the timing, okay? They come very late. Please start from the beginning, okay? Because of you, one buddy is late, and he wastes the time for all the other students, okay? So please don't do these things. Anyways, today we will discuss about DAC specifications, okay? What is the meaning of DAC specification? DAC specification means that when you guys when for example we have one application and we are selecting one digital to analog converter, what are the specifications that we shall consider, okay, for selection, okay? What are the specifications? Okay, if let's say for example I have a project and I have to use one digital to analog converter, okay, I want to select one, okay, so what are now there are multiples available, so multiple available. Please let me just discuss this one. Second problem is the same as first problem, okay? Just focus here, my friend, okay? So what we need now, that what are the parameters that are important for us to evaluate the performance of any digital to analog converter, and based on those parameters specification we choose our digital to analog converter, okay? What are those specifications or manufacturer specifications that are important? So we have resolution, which is again the step size resolution, okay, percentage resolution, accuracy, okay, offset error, and settling time, okay? These are the different things that are important, okay? So first of all resolution. We all discuss resolution in detail, okay? We all discuss resolution. By the way, it is not resolution, it is percentage resolution, okay? Here, this one is percentage. We are discussing percentage resolution. This is not resolution, percentage resolution, okay? So we know resolution, we know percentage resolution, how to calculate. But when I consider any DAC, when I consider any DAC and I see the specification, then I will be given the percentage resolution, and that will be given as number of bits, okay, in the specification sheet, okay, of any DAC. When I will go in the market, I will select any specification from the manufacturer. Manufacturer will provide me the specifications in the specification sheet. How will I know? Simply the number of bits, okay? Not all those calculations that we have done, no. It will be simply number of bits. So I will see what is number of bits. Based on that one, they will define, usually the manufacturer, they define the specification based on the number of bits, okay? So it is simply nothing but the number of bits. So here we see DAC or resolution is number of bits, okay? Number of bits, you can see here number of bits. I'm talking about the specification sheet, okay? Then we have accuracy. What is accuracy? In the accuracy we have two types of things, okay, in the accuracy. Yeah, whatever, you know, percentage resolution or resolution. I am talking about the specification sheet, okay? Not what we have done till now. In the specification, for specification only, okay? For specification sheet, from manufacturer, okay? How will I know? By number of bits, okay? Very simple, okay? I will go to the manufacturer, I will see his sheet, and I will be given the as number of bits, okay? Now for the accuracy we have two errors. One is called the full scale error, and second is called the linearity error. Okay, for the specific this one accuracy. Okay, now what is full scale error, my friend? Here, full scale error is very simple. Full scale, and there is a calculation for the full scale error. We will see. Okay, so full scale error is the maximum deviation. Deviation means the difference. Okay, difference of the DAC output from its expected value. Okay, we have one expected value, but we have a different output, so there will be error. Okay, that is called error. And when we express is at percentage of the full scale, means I have that I will calculate that error. Okay, means I have an actual value, a DAC value, output value, and I have an expected value. So I will calculate the error and I will express is as percentage from the full scale. Full scale will be given or I have to calculate, and I will I will express it as the percentage, that is called full scale error. Okay, so maximum change or deviation of the DAC output from the expected value, we will do it. Okay, don't worry. Okay, we will see how we do it, and expressed as the percentage of the full scale. Okay, then we have linearity error. Linearity is the error in the step size. Okay, so full scale error is the error in the analog output. Okay, is the analog output full scale error, and linearity error is the error in the step size, error in the step size. Okay, yes, error in the step size. Okay, so you should understand. So one error is in the output, analog output, and one error is the step size. So which error we're talking about? Full scale error is the error in the analog output, and linearity error is the error in the step size. So these things are provided in the specification sheet from the manufacturer. Okay, I know this DAC is from a certain manufacturer. I will go to his specification sheet and I will see number of bits. It will define the resolution. Okay, very simple. I don't need all those calculations that we have done in the past. Okay, I will simply see number of bit that will define, because you know percentage resolution is depend upon the number of bits, right? So therefore they say that DAC resolution in the specification sheet is simply the number of bits. And then for the accuracy, we have two errors: full scale error and the linearity error. Full scale error is the error in the analog output. Okay, and you expressed in terms of the full scale, and the linearity error is the error in the step size. Now let's see the calculations. How do we calculate? Okay, so we will do the calculation next page. Okay, see the next page. Okay, before I discuss the offset error and settling error, I will discuss this example. Okay, okay, here sorry, not this one. I will discuss this example. Okay, this example. Okay, so what is this example? Very simple. A certain 8-bit DAC has a full scale output. We all know what is full scale output: maximum or full scale or reference output, okay, of 2 milliampere, and a full scale error of plus minus 0.5% of full scale. Okay, what is the range of the output for the input? This one. Okay, now you are given a full scale output. Okay, and we all know that the full scale output, if we are given the full scale output, I can easily find the step size. Why? Because the step size is equals to what? Analog output over digital input. Now if I have a full scale, we know for the full scale What will be the input? Input will be all ones, right? Which is what? Which is what? 255, right? Very simple. So what is step size? Step size is, I am given 2 milliampere is the full scale over the input. Okay, 255. I got the step size, which is how much? 7.84 microampere. Okay, now it is telling you that what will be the range of the output. Why it is asking you the range? It is asking you the range because it has given you the error. Okay, asking you the range because there is an error. Okay, which is percentage of 0.5% of the full scale error. Okay, it has given to you. Before the error, I will find the ideal output. Okay, very simple. And we know what is the ideal analog output. What will be the analog output? Analog output equals to K times digital input, right? Now what is digital input? Digital input is given to you 100000. Okay, this one, right? And this is equals to 128, okay, in decimal. So very simple. Our analog output, if I say ideal, analog output ideal without any error. Very simple. Okay, I know it will be K times digital, right? What is K? We already find 7.84 micro, okay, micro times input is how much? 128. Okay, based on this, what I got equals to 1004 microampere. Okay, microampere. Now this output is ideal. Up till now what we have done is the same that we did before also, right? Okay, there is no difference, but this is the ideal output. Now we are given an error. Okay, what is the error? It is a full scale error that we see the definition, and it is how much? 0.5% of the full scale. Clear? So now it is very simple. Okay, what is the 0.5 of full scale? Now what is the full scale? Full scale is, so 0.5%, you know, percent, when we multiply, convert the percent, we divide by 100, right? Times, what is the full scale? 2 milliampere, right? Clear, everybody? 0.5% of the full scale. So how much we got? We got it plus minus 10 microampere, because the error can be up or down. Okay, plus or minus. So now very simple. What is our ideal output? The ideal output is 1004 microampere plus minus 10 microampere. Very simple. So again, first you find the ideal output. Okay, again, first you find the ideal output, then you find your error and you add the error. So 1004 minus 10 microampere minus 10, 1004 plus 10, that will be your range. Clear, everybody? Okay, everyone? So first find the ideal, then find the error, okay, given to you, calculate the error, and then you find the range. Very simple. Okay, look again very carefully and ask me any question. So this is the way we got 10, because what is the full scale error given to you? Full scale error, it is telling you 0.5% of 0.5% of the full scale, right? So what is 0.5? 0.5%. When we can convert percent, we divide by 100, right? Very simple. times what is full scale? 2 milliampere. Clear? So it comes how much? 10 microampere. Like this. So simple. Okay, so it is plus minus 10 because we need a range. Clear? Okay, everyone. Okay, so this is the way you are given the error. You are given the error, percentage error. From the percent error, you will first of all find the ideal output. First of all, given conditions, find the ideal output. How you will find the ideal output? The same way that we have done in the past 2 weeks. You will find the step size, you will find the output, okay, be given the input, okay. This is the same thing. Then you will find out what is the full scale error, calculate the full scale error, and you will find the range of the output. This is how the questions will come regarding the full scale error. Okay guys, now we have one more error which is called offset error. What is offset error? Very, very simple. Offset error is like, you have a gauge, a pressure gauge. If I don't apply any pressure, what should be the what it should give me? Guys, if I don't apply any pressure in the pressure gauge, what it should give me? 0, right? Okay. Yes. Okay. If it is not giving 0, if it is not giving 0, it means there is an error, right? That is called offset error. That is called offset error. So if I have if I have a DAC, okay, ideal DAC. Okay, what should I have? If I have the input zeros, all the inputs are 0 bit, okay, the output should be also what? Analog output voltage should be 0 volt, right? But if it is giving you some output, it means there is an error. That is called offset error, okay? So look definition, what it is telling you. Ideally, the output of a DAC will be 0 volt when the binary input is all zeros. In practice, however, there will be a small output voltage for the situation. This is called offset error, okay? And if we don't correct this offset error, it will be added to all the output, okay? All the input cases, whatever the output, it will be added, okay? So we have to make external. So many DAC have external adjustment, okay, initial error you can say, okay. So many DAC have the external adjustment, okay. So you can make to remove the offset error, okay. And you are given a question here in the second example. Now look this example. So a 4-bit DAC has an offset error of 2 millivolt. So you are given an offset error here. See, offset error of 2 millivolt, okay, and a perfect step size of 100 millivolt. Find the ideal and actual. Ideal and actual, okay, and you are given the inputs, okay. You are given inputs, you are given input, okay, you are given the inputs, and you know the step size. We all know how we'll find the formula. What is the formula? Analog output equals to K times digital input, right? Right? Okay. So from this formula, I will find all the ideal output. Okay, all the ideal output. You can see step size times digital input. Okay, all the ideal outputs. Clear, everybody? Now you are given an offset error. So very simple. What will you do? You will simply add the offset error here in the ideal. So your ideal output was 0 millivolt. You add the offset error, it becomes 0 plus 2, which is 2 milliampere. You got the output 100 millivolt, you add the offset 2, you got 102 milliamp volt, 802, and so on and so forth. It is so simple, okay? So you apply, simply you find the ideal output and you find the input, okay guys? So this is the way. The last thing here is called settling time, okay? Settling time. So settling time is what? Settling time is very simple, okay? Settling time, because you know now you have the input and you should have the output. Now for any DAC, it will not immediately give the output, okay? You provide an input, it will take some time. Ideally it will not give you in just like this, okay? It will take some time to give you the output, okay? That is called settling time. Means how much time DAC takes to that you get an digital input and you get the output, okay? That is called settling time. We call it operating speed. So you can see here, one minute. Okay, as said, this one is always we add the offset. You can see plus minus, no problem. Okay, you want. Okay, the only idea is it is an offset error. Okay, it will be plus or minus, whatever. Okay, don't worry about this. Okay, you can plus or minus. Now, just please, guys, focus on now the settling time. Okay, settling time is the operating speed, as I said to you, that you have an input and you have to find the output, okay? A digital input output. It will take some time to give the output. It is called settling time. So we call it operating speed. So typically how much it is? It is 50 nanosecond to 10 microsecond, okay? That is called settling time, the time it takes to give the output, okay? So I'm writing here, settling time is what? The operating speed of DAC is called settling time, which is time required for the DAC output to go from 0 to full scale, as the binary input is changed from all zeros to all one. So if I have the input all zeros, 0, 0, 0, 0, 0, 0 to all ones, 1, 1, 1, 1, 1, 1, it will, in the output it will change from 0 volt to the full scale volt, right? That is called settling time. So typically it tells you, this time tells you that how much time it will take to give the output, okay? It is called settling time. So this is the definition, my friend, for settling time, okay everybody? So we have, these are DAC specification as we discuss. So what we discuss about the resolution in a specification sheet. Resolution is nothing but number of bits. Then we discuss about the full scale error and the linearity error. Then we discuss about the offset error. Then we discuss about settling time, and then we solve the two questions, okay everyone? Now tell me, do you have any question up till now? Yes, everyone. Please tell me before we move forward. Any question, guys? Please go through yourself and tell me if you have any questions. Check. Anything you know and you want to ask? Full scale error and what? Linearity error. Look, linearity is error for the step size. Full scale error is the error of the output, okay? And offset error is also the output error, but it is the initial error. Simple. So again, full scale error is the error in each output, okay? Linearity error, yes, you can add or subtract, don't worry about this one, but usually what we say offset error is plus, okay? We can say plus minus, don't worry about this one, okay? Yeah, you are right, offset error can be plus or minus, okay? Don't worry about this, okay? But here we assume that it is an offset error is plus, okay? Only for the assumption base. Okay, but you add only, I will make it correct. Okay, the idea is you should know that the initial error. So guys, again, full scale error is the error in each one. Okay. Okay, why having less k is better? Because you will get more accurate values. I always give example of the this our pressure gauges. Okay, like you have two pressure gauge. One pressure gauge has 0, then 5 psi, 10 psi, 15 psi, and so on. But another stage is gauge. It show you 0, 1, 2, 3, 4, 5. Which one is better? The second one, right? Because you can see more accurate values. This is the advantage. If I have less k, less step size, the resolution is better. The resolution is better. Why? Because I can see more accurate values. Clear? Okay. I can see more values. But if I have 0, 5, then I don't know how I will see. I have to make a approximate 2.5, for example. Okay. But if I have 0, 1, 2, 3, I can accurately find out a particular value. Okay. Therefore, less k is better. So now, okay, one person he asked me, brother Abdullah, he asked me difference between the full scale error and the other one. So full scale error again is the error in each output. And even the offset error is also the error in each output. But offset error is the initial error because you have some problem in your external, which will be fixed by the external instrument. And full scale error is the internal inhibited error, which is depending upon the values. Okay, full scale value. Okay, so and linearity error is the error for the step size. Okay, okay, everyone. Now, after that, we have these two pages. Everybody, please go through these two pages. Okay, I will not discuss these problems. You can just go and check yourself these two. Okay, this is the like a handout. It will help you for preparation for the quiz. Okay, or this one will help you for the preparation of these 3 pages. Okay, 1, 2, 3. Okay, these 3 pages we have a lot of questions here. Just go through. Okay, they are very simple. I have discussed already those things, so you should not have any problem. Okay, now we have the most important part. So we have finished up till now and digital to analog converter. There was one question, one student, he asked me that teacher, you did not discuss this problem. This one I discussed already. Okay, but anyways, I will discuss again. Okay, yes, I discuss again. This one, it gives you the relationship between the LSB resistor and the MSB resistor for our DAC using binary weighted. If you remember, we have discussed this one, right? This one. Okay, so one is the first one is the MSB resistor, this one is the MSB resistor, and this is the LSB resistor, right? What is the relationship? Okay, so the relationship is based on this formula, okay, 2 to the power n minus 1 times MSB. So the same thing, you will apply this formula. Okay, apply this formula in this problem and you will find out. Okay, now depending upon what is given to you, you are given MSB resistor and you have to find LSB, so you will and the number of bits. Okay, you will apply this. If you are given LSB resistor, okay, again, if you are given the LSB resistor and you have to find the MSB, you will only divide it by 2 to the power n minus 1. Okay, it will be on the top. So depending upon, okay, what you have, and I explain in detail why it is 2 to the power n minus 1, because remember for the 4 bit it was 1 kilo and 8 kilo. Okay, when we discuss here, when we discuss this one, for the 4 bit it was 1 kilo was at the MSB and 8 kilo was LSB. Okay, so which is what for 4-bit. Okay, so therefore it 2 to the power n minus 1, so 2 to the power 4 minus 1, 2 to the power 3, which is 8. Okay, so this is the reason that we have this formula, which is 2 to the power here 2 to the power n minus 1. This is the reason we have 2 to the power n minus 1. N is on the top. Clear, everyone? Okay, so we discuss all these things. All this one you will study yourself. Now come back to now. So we finish now. Up till now we finished digital to analog converter. Okay, we have to start now analog to digital conversion. Okay, we have to start now analog to digital conversion. Okay guys, now analog to digital converter is a very typical, I have to explain to you. So let me just do one thing. Please just wait guys. Okay, let me just actually I'm doing something because I need to explain it in detail and it is not showing properly, this diagram. It has to be very clear. Okay, so let me just share it here. So here we have okay. Okay guys, so look this diagram. Okay, this is an ADC. Okay, we call it ADC. Please open your handout also in front of you, and now I will explain to you. Okay, and this one I just wanted to make it because I want to make it very clear. Okay, everybody with me? Okay, now look, understand very carefully. First of all, what are the components in this one? So we have 4 components in this one. Okay, this is called analog to digital converter. Okay, where is, first of all, where is the input? Analog input. Analog input is provided from here. Okay, where is the digital output? Digital output is here. This is digital output. Okay, so analog output, digital out, input and digital output. Okay, now we have the total, we have 4 elements in this one. First is control and gate. Second one is D to A converter. Therefore, I told you why we studied D to A converter, because in the ADC, digital to analog converter is one element. Okay, so this is the reason I cannot study ADC before. Okay, I need to first study DAC, then I will be able to study ADC. Okay, so we have digital to analog converter. Then we have a counter. This is our counter. 4-bit binary, simple binary counter. Okay, and then we have a comparator. So I have 4 elements. Number one, control and number 2. So number 1 we have control and. Okay, this is control and this one. Number 2 we have a digital to analog converter. Number 3 we have what is comparator, and number 4 we have counter. Okay guys, so now how does it work? Understand it very simple. Okay, understand it very carefully. Okay, so first of all we have a start pulse. So we have checked this start pulse here. Start pulse has two things. It goes up and then it goes down. Okay, when it goes from 0 to 1, okay, start pulse go from 0 to 1. What happens? This one will go to reset, so the counter will be reset. Counter reset means initially all will be 0 0 0 0, right? And this one will go to also here. When it goes to an AND gate 0, we know an inverter, we have inverter here. So inverter, sorry, we have a inverted here. Okay, so when we have this element from 0 to 1, okay, 0 to 1, this is start. Okay, so this one is going in 2 places. This is going to 1 here and it will come 1 here. Okay, when this one will come here, this will reset the counter, so counter will be all 0. Okay, we know that. But when this one comes here, okay, we know the invert, it is a bubble, so here the output will be 0, right? And we know that if any AND gate output is 0, always be 0, so you will have nothing but 0 here, right? So any clock, will the clock go? No. Okay, and initially we have this is the 0. Okay, this this is the counter is zeros, all zeros. Okay, all zeros, and digital analog converter, and we know this is called VAX. So we are comparing here two outputs. We have VA, the original inputs, and we have VAX. This VAX, what it is doing, it is the output of from the digital to analog converter. Okay, from here Okay, so this VAX is actually equal to size times digital input, right? Whatever the step size times digital input. So what we are doing now, initially what will be VAX? VAX will be 0. Why 0? Because initially the counter is what? All 0, right? So counter is 0. So, and you know, your 0 times K will give you the 0 output, right? So you have, now this is comparator. This is comparator. What comparator does? Comparator output is, the comparator operation is very simple. If you have, the comparator says that if you have plus, if plus is more than minus, the output is always 1. And if plus is less than minus, the output will be what? The output will be 0. Okay, so here it is 1 initially. Why? Because VAX is 0. Okay, VAX is 0. Initially VAX is 0. Okay, so we are getting 1. Okay, so this is 1, but here since it goes from this start pulse, it goes from 0 to 1. So this one comes here, this counter reset, but when this one comes here, this one get 0, and we know that the AND gate, if any 0, the output will be always what? 0, right? Allah, the output will be always 0. So you have, this is 1, this is 0, so the output will be always 0. Okay, so you will not get any clock. Okay, now, so this is happening initially. Now what happens? And this is also, this is 1, this is clock, but since this is 0, it's always 0. Okay, now what happens? When in the start pulse, it goes start pulse. Now next, when it start pulse, next it goes from, in this second pulse, it goes from 1 to 0. 1 to 0. What happened now? 1 to 0. Now it will not reset, right? Okay, it is 0. So your reset is not active now. Okay, now it means now counter can change. Counter can count. Okay. Now this 0 will come here. So here it will become 1, right? And it was already 1. So what happened now? So this is 1. So this is 1. This is 1 because we have 0 pulse. Okay, we have 0 pulse, we have 0. So this becomes 1, this becomes 1. So very simple, the clock will start coming here. When clock will start coming here, what will happen? This counter will start counting. Clear? So it will count 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 and so on. It will start counting. This VAX will start incrementing. Why? Because it is what? K times digital input. Clear? Okay. So this is 1, this is 1. Clock start coming. Okay, it start increasing. VAX it start increasing. Now VA is constant, right? Because it's the digital input. When VAX will cross VA, so means plus becomes less than minus, means minus becomes more. What will happen at the time? It will become 0. So it will become what? the clock will stop coming, it will become 0 and counter will stop. Okay, when the counter is stop, at that time you will simply take what is the output. Okay, that will become your, you will see what is the value of digital, that will become your output. Clear? Let me just discuss again so you understand it all again, guys. Okay, first of all, we have how many we have this one. First of all, we have how many components? Number one, we have control and, okay, yes, control, and we have a counter, binary counter, very simple binary counter, which depends upon, so we have control and we have binary counter. This counter depends upon the clock input will come, it will count, very simple, 0 0 0 0 0 0 0 1 and so on. Then we have digital to analog converter. It does nothing but it has the input, digital input from the counter, and it gives a dummy output. Okay, this dummy output we keep just only for the comparison, for the comparator, DVAX. Okay, K times digital input. Okay, and then we have VA. So we have then a comparator. What is the purpose of this comparator? If the VA is more than VAX, it will be 1, and when VA become less than VAX will be 0. Clear? Okay, so this is the arrangement. What happened initially? Initially what happened? This is it controlled by the start pulse. Initially start pulse goes high, then start pulse goes low. So when it goes high, what happened? This is 1, 1 will come here, become 0. This is 1, but since it is 0, so it will be always give you 0. In the meantime, this 1 will go here as well, so it will reset the counter. Okay. Next, then start pulse go from 1 to 0. When it goes from 1 to 0, this 1 will become 0. So this 0 will become what? 1. When it becomes 1, this is 1, this is 1. The clock will start coming inside. Clock start coming inside. The counter start counting. Okay. Okay. Going up counting. And VAX will start incrementing because it is what? K times digital input. So counter will start counting unless VAX, this becomes more than VA. So when this becomes more than VA, I told you it will become what? 0. So when this 0 will come here, this will stop working. At that time, whatever is here is our output. Okay, everyone, do you understand? Do you understand, guys? Okay, we will see the example now. Okay, okay, now let's see the example now. So go back to our this one. It will be given to you in the exam. Listen, we will see one example now, you will understand. Okay, don't worry, guys. So we have look this example now, very simple example. Okay, this example. Okay, let me just do one more thing. So we have guys, you just first of all see what I have discussed. Let me just do something because this example I want to make it bigger, okay? Okay, so now let's see. Hello, Akhi, आवाज is the sound is there. Okay, now just 1 minute. Okay, guys. Wait, guys, wait 1 minute, wait. Hello, everyone. Okay, I'm sorry, but just wait, please. Please wait now. Okay, now please look here. Look now this example. Habibi, now please, I'm sorry. Look this example now. Okay, this example is now the same example. Your VA, hello, Muhammad Yusuf, Lahya Mayatla Andi. Listen, Habibi, guys, can you hear me? Sort is quiz. Ish mushkila sort. Okay, guys. Now please look here. Now keep that example in front of you and look this example. Okay. You are given a VA. VA will be given to you. You are given 4.9 volt. Number of bits will be given to you 4 bit. And step size will be given to you 0.5 volt. Okay, these 3 parameters must be given to you. Okay, so you have VA. VA we know which is the analog input. Okay, we know number of bit which is 4 bit, and we are given the step size K which is 0.5. Okay, so initially, now as I said to you, we will compare VA and VAX. Okay, we have two in the comparator. We have two things in the comparator, VA and VAX. Okay, VA is the input, VAX is coming from digital to analog. Brother Muhammad Yusuf, what can I say? Wallahi. Guys, can you hear me? Enable your audio, ya akhi. Muhammad Yusuf, enable your audio. Okay, then you can hear. Okay, enable. Okay, remove the headphone. Just listen to you guys. Okay. So in the comparator, I told you the comparator is the one which is controlling the operation. Comparator, we have two inputs. VA, which is the given digital analog input, okay, and VAX and VA are the input in the comparator, okay. So VA is the analog input which is given, okay, given, and VAX is coming from where? Coming from digital to analog converter, okay. Okay, so VAX will keep increasing. I told you, keep increasing, okay, unless VAX will become VX will become more than VA, or I can say that initially what we will have, VA will be more than VAX, right? So VAX now increasing, and when VA will become less than VAX, what will happen? The output EOC will be 0 and of conversion will be 0, and our this one counter will stop counting. Okay, this is what we see, right? Okay, so it is given to you in the example. Now see, because of this one, see the example. So you are given VA is 4.9 volt, okay, the input, okay, number of bit will be given to you, and wallahi ya akhi, what can I say? What can I say, my friend? Okay. Udil, wallahi, what I cannot say anything. Anyways, I will recording will be there. Don't worry. Okay. You can see recording. Okay. Okay, you can see recording later on. Okay. Later on. Later, okay, I will share. Wallah, guys, voice is not clear. Guys, voice is not clear. Any problem? Okay, now listen. So please now look here. Very simple. Let us go fast now. Okay. So VA is given to you. You will know the number of bits and you know step size. Okay, very simple. So initially you have 0 0, counter value is 0. Okay, VAX, what we told, VAX will be K times digital input, because it is output from the digital to analog converter. Okay, this is okay, step size times digital input. So 0.5 times 0 will be 0. So VA is more than VAX, it will keep counting. Okay. So clock number 1, it will become, the next clock will come, it will become, now clock is coming, right? I told you, clock keep coming and it will count. Okay, counter will count. 0 0 0 1, 1 into 0.5, 0.5. Still VA is more than VAX, it will counter will keep on counting. Okay, because EOC still is what? EOC is 1. Okay, is 1. So counter keeps counting. Okay, okay, from the AND gate. Now clock 2 0 0 1 0 2 into 0.51 volt, same as above, unless clock number 10. As clock number 10, what will happen? 1 0 1 0, right? Which is what? 10, right? 10 times input, digital input is 10 for the digital analog converter, and 0.5 is your what you call it, step size. So you got how much? 5 volt. Okay, now VAX EOC is, you can check here, EOC is the output of the comparator, yahi, which has to be 1. Okay, if it becomes 0, khalas, Okay. Yes, okay, okay. Okay. So now VAX is more, VAX becomes what? Less than VA, right? VAX becomes more than VA, right? Okay, because it is 5. 5 becomes more than 4.9. Okay, or we can say VA becomes less than VAX. So what will be the counter output? Sorry, what do you call it? Comparator output. So comparator output, which is what? EOC will become what? 0. Now this 0 will go to what? Will go to the AND gate, right? Okay, so the output AND gate will become what? Output AND will be 0. So counter will stop what? Counting. Khalas. Okay, everyone, counter stop counting. Okay, so this is the way it works. So at the time we will see what is the output, 1010, that will become the output. Okay, so this is the way, guys, it works. Okay, step by step. Okay, everybody, understand? Any question? Any question? Okay, so again, please go through the example and you will understand it is very easy, by the way. Okay, now the last thing today that we have to discuss is okay, so this is the way we have the output. Okay, so as I explained you here, I explained you the full operation, guys, full operation, how it works, and then we discuss one example. Okay, okay, and final output is what? 1010, because at that time it will stop. Okay, okay, at the time it will stop. Okay, guys, now look, one question here. Okay, this problem, okay, this problem is very simple. Okay, up to here we will see, up to here, this problem. Okay, leave this one up to here. Okay, this one we will discuss in next class. Okay, anyways, so the in the guys, my good friends. Okay, let's stop here. We will stop now here. Okay, I don't want that I make a lot of discussion and then we have a problem. Okay, we still have time. Okay, we will stop here now. We will stop here, guys. Okay, and what we do now, next week again, quiz. Okay, yes, quiz till here. Okay, and